All right. So, this is active filter design, lecture 8. In the last class, what we saw was the following. We are attempting to realize an LC network implemented as a ladder, right, that realizes the desired transfer function, which means that we exploit the fact that looking in here, whatever power is dissipated, it must all be being dissipated in the load resistor Z0. Therefore, we have Vi square by 4 Z0, which is the maximum power that can be drawn from the source, right, which is therefore also equal to the maximum power that can be dissipated in the load. And we know that thanks to the LC network, the power dissipated in the load cannot be equal to this maximum for all frequencies. That is the job of the LC network. It is making the power dissipated in the load close enough to the maximum for some frequencies, that is all frequencies in the pass band, and making sure that the looking in impedance is such that only very little power is being dissipated at frequencies outside the pass band. So, we said that therefore, the looking in impedance Zin of S, okay, is something which changes with frequency thanks to the LC network, and at frequencies where Zin of S is close to Z0 in some sense, the power dissipated in the load resistor Z0 is maximum or close to the maximum possible, and at other frequencies the power dissipated is smaller than the maximum possible. And this notion of closeness to Z0 is quantified by the so called reflection coefficient, and the analogy is actually quite physical in the sense that whenever you have what do you call a system, I mean with this happens in a whole bunch of physical scenarios when you are dealing with waves, right. For example, when you have a glass plate, you shine some light on it, obviously not all the light is going across the plate, some of it is getting reflected back. Okay, so that's the physical interpretation of the reflection coefficient. So, the power actually dissipated into the load is the maximum power available times 1 minus mod gamma square, where gamma denotes the reflection coefficient, and this power must be equal to Vo square by Z0. Therefore, mod of Vo by Vi is a whole square is 1 by 4 times 1 minus mod gamma the whole square. Does this make sense? Okay, this is just a review of what happened yesterday, and therefore, this gamma which we saw yesterday to be equal to Zin minus Z0 divided by Zin plus Z0, as we expected, denotes a measure of how close Zin is to Z0. In particular, when Zin equal to Z0, gamma is 0, and that is the familiar matched condition as they call it, okay, because all the available power from the source is absorbed in the load and none of it is reflected back. And please note that at the maxima of transmission of the filter, what happens to, what can you say about gamma? Mod gamma, and therefore gamma is 0 at the maximum of transmission. Similarly, mod gamma is small in where? Either has to be pass band or stop band. What is it? In the pass band. Very good. Okay. What other observation can you make? Mod gamma is approximately 1 in the stop band. And as a final this thing, mod gamma is exactly equal to 1 where at infinity, of course, but anywhere else you think? At the zeros of transmission, yes. For all pole filters, the zeros of transmission just occur at infinity. So mod gamma only goes to 1 at infinity. On the other hand, for the other approximation we saw, that is the inverse Chebyshev approximation, we saw that there are finite zeros of transmission, which means that the mod gamma will actually touch 1 at those frequencies. Is that clear? All right. So the way we like, so this suggests a way of realizing the network, and that is from mod h of j omega square, you get mod gamma square, right? Where this is all evaluated on the j omega axis. From mod gamma square, you get gamma of s times gamma of minus s. Okay, and from gamma of s, what do? You find Zn of s. Okay, from Zn of s, you find the network, right? Given that we want a ladder. All right. Okay. Now, and how did we do the ladder? This was the source. Right. So what we will get first is, depending on which sign you choose for gamma of s, you will end up with Zn of s either having the numerator degree being greater than the denominator, or the numerator degree being smaller than the denominator. Please note that since Zn of s is a physical impedance, the difference between the degrees of the numerator and the denominator can only be plus or minus 1, okay, because any physical impedance Z of s, as s tends to infinity, will either look like a inductor, a capacitor, or a resistor. So the absolute the absolute value of the difference between the degrees of the numerator polynomial and the denominator polynomial cannot exceed 1, okay. And in this case, we see that at infinity the network, looking in at the red arrow, behaves like an inductor. Therefore, this will correspond to the situation where we take the gamma of s, where the numerator is of the form s to the power, in the Butterworth example we took yesterday, was plus s cube divided by d of s. Okay. Now, so Zn of s, therefore, will be SL1 plus Zn, then I will call this Zn1, right, plus, so Zn of s must be SL1 plus Zn1 of s, okay. But Zn1 of s is nothing but as you can see, the shunt combination of C2 and the rest of this beast, correct. So this therefore can be written as SL1 plus 1 by Yn1 of s, okay. And what is Yn1 of s? SC2 plus, yeah, very good. So Yn2 which therefore, I mean, so now you see the way things are proceeding, it's 1 plus 1 by SC2 plus 1 by Yn2 itself is realized as a series combination of stuff. So this is 1 by Zn2 of s, which is therefore given by SL3 plus 1 by blah blah blah. Okay. So at every step of the way, what we like to see, this suggests the following, that is, to find L1, what do we do? I mean, equivalent, I mean, we are setting Zn of s to infinity. I mean, we are setting s to infinity and seeing what happens to Zn of s, and we are setting Zn to s to infinity on the right hand side also, and we are exploiting the fact that Zn1 of s tends to 0 as s tends to infinity. That is what we are doing, correct. So, I mean, if Zn1 of s does not tend to 0 at s equal to infinity, then you cannot get L1. Okay. In other words, this L1 is simply the residue of Zn of s at its pole frequency. Does that make sense? At the pole frequency of Zn of s, or at the 0 frequency of Zn1 of s. You understand? So, is this clear? See, as s tends to infinity, what happens to this character? What happens to Zn1 of s as s tends to infinity? It goes to 0. So, therefore, Zn of s is nothing but, I mean, L1 is nothing but the residue, okay, of Zn of s as s tends to infinity, and we are exploiting the fact that at the pole of Zn of s, Zn1 of s has a 0. Okay. If Zn1 has a 0 at infinity, then Yn1 of s will have a pole at infinity. So, in the next step we are removing that pole and looking at the what is left, okay, and that will have a 0 at infinity, and therefore when we that's an admittance. So when we look at the impedance, it will have a pole at infinity, and this is what is called the ladder development of the impedance. You understand? Okay, so let's now, we also know that mod h of j omega square cannot be greater than 1/4, because that is the reflection coefficient cannot be smaller than its magnitude cannot be smaller than 0, which means that if we are in a situation where the maximum power is being drawn from the source, that can only be v square by 4z0, and that is completely getting dissipated in the load, which means that the maximum voltage gain from input to output cannot exceed half, and that's not too big of a problem, simply because the peak magnitude can be scaled down to half. Okay. So this basically means that for an equally terminated ladder, also sometimes called the doubly terminated ladder, you can realize even and odd ordered Butterworth filters. Okay. You can also realize odd ordered Chebyshev filters. Even order Chebyshev filters obviously cannot be realized using a equally terminated structure, because at DC the gain is less than half, okay, which means that the the maximum possible the maximum is should be half by physical constraints, but in a even order Chebyshev, the maximum of transmission is not the value of the transmission at DC. Okay. So an engineering solution to this is to say, hey, I will stick to we know that if you want to design a 4th order Chebyshev, a 5th order Chebyshev will do better than a 4th order Chebyshev, which means, and I know how to realize an odd order Chebyshev, so I will stick with only odd order Chebyshev. An alternate thing to do is, if you are forced to do an even order Chebyshev, is to actually not have equal impedances on the source and load. The two impedances have to be different. Okay. I will come back to that if I have time, but for the time being, let's continue on with synthesis for the. So Butterworth is done, odd order Chebyshev is done. Okay. What we need to do is next is realization of inverse Chebyshev. Yes. Okay. So what is so different between the inverse Chebyshev approximation and the Butterworth and Chebyshev approximations? So the key difference between as far as transfer function is concerned between the inverse Chebyshev approximation and the Butterworth approximation or the Chebyshev approximation is that the inverse Chebyshev has got finite zeros of transmission, right, which basically means that a network which realizes a ladder network which attempts to realize an inverse Chebyshev filter cannot be something like this. For example, a third order Chebyshev or Butterworth look like this. A third order inverse Chebyshev cannot look like this because all the zeros of transmission of this network are at infinity. So if you want to introduce a zero of transmission, what could you do? Yeah, so you can do it in many ways. One way of doing it is to do this. So at the zero of transmission, what happens? What is the impedance of a series LC circuit? It's not zero. I mean, it's only zero at one particular frequency. The resonant frequency of the, pardon? Yeah. So that goes to zero. A series LC circuit impedance goes to zero at 1 by square root LC. Okay. Similarly, a shunt LC network's impedance goes to infinity, or it becomes an open circuit at the resonant frequency. Correct? So this is one way of introducing a zero of transmission, okay, in the network. Does it make sense? So an alternate way of doing it would also be the following. This is that capacitor first network. Did you just come in? You can't see. Okay. So this is L1, this is C2, L2, L3, this is C1, C2, C3, L2. So in this case, we see that the L2 C2 network becomes a short circuit at what frequency? 1 by square root of L2 C2, and in this network the series arm becomes an open circuit at 1 by square root L2 C2. Okay, and if you kind of stare at the passive ladder, that the all pole ladder, the zeros of transmission were all being realized by what? Either the series arm becoming a short, or the shunt arm becoming a short, or the series arm becoming an open. So at zeros of transmission of the ladder, which are all at infinity, what is happening? The series arms are all becoming open circuits, and the shunt arms are all attempting to become short circuits. Right? That's the same idea here. The moment you have a finite zero of transmission, instead of the transmission of the filter going to zero at infinity, if it happens at a finite frequency, then the series arms should become a short circuit at, the series arms should become an open circuit at the zero of transmission, which is given by a parallel LC network, or the series arm should become, or the shunt arm should become a short circuit at the zero of transmission, which means that you replace, instead of having a capacitor, you replace it with an element which goes to whose impedance goes to zero at a finite frequency, and that is a series LC network. Is this clear? Yes, no? Okay. Now the question is, how do we go about synthesizing this network or the other one? Okay. Again, we proceed in pretty much the same fashion. Please note that again, the network enclosed in the box, in the green box, is a lossless LC network terminated in a resistor. So in both these cases, all the theory that we have developed still remains largely the same. Correct? So from the magnitude squared response, you can get the magnitude squared of the reflection coefficient. From the magnitude squared of the reflection coefficient, you will be able to get gamma of S, which will in turn lead to Zn of S. from which we now need to synthesize this network. So, up to getting Zn of S, the procedure is the same as before. So, let me take an example. For the inverse Chebyshev, what is the magnitude squared response? It's epsilon square Cn square of 1 by omega divided by 1 plus epsilon square Cn square of 1 by omega. Correct? And clearly, what is the maximum value of this transmission? What is it now? It is 1, and clearly if you want to have an equally terminated ladder, having a maximum transmission of 1 is not possible. So, what should we do? I will make this, I will divide mod h of j omega by 2, which means mod h of j omega the whole square is 1/4 times epsilon square Cn square of 1 by omega divided by 1 plus epsilon square Cn square of 1 by omega. And this, as we have discussed, must be 1/4 times 1 minus mod gamma the whole square, which means this and this go away, and we are left with mod gamma square is nothing but 1 minus epsilon square Cn square divided by 1 plus epsilon square Cn square, and what might that be? 1 by 1 plus epsilon square Cn square of 1 by omega. All right, which means gamma of S is therefore, what is gamma of S? Please note that this, how will you, you have to now factorize that as find the roots of that polynomial. There will be 2n roots. You collect the roots in the left half S plane, multiply out the factors, blah blah blah. So, what is that? Pardon? This is a standard inverse Chebyshev denominator, which can be obtained by taking the Chebyshev denominator and flipping the order of the coefficients, or in other words, you take the Chebyshev denominator, right, replace S with 1 by S. So, this will now be the Chebyshev denominator with 1 by S instead of S, okay, and then to get everything as a polynomial in S rather than a polynomial in 1 over S, what will you do? You multiply the numerator and denominator by S to the power n. So, what will you get in the numerator? You will get S power n divided by d of S. Correct? D of S is the usual inverse Chebyshev denominator, where d of, what should d of 0 be? Sorry, what should d of infinity be? Wait a minute, that's not what I wanted to ask you. Yeah, I'm sorry. This is just the standard Chebyshev, inverse Chebyshev denominator. All that you need to do is you got to make sure that the peak value never goes beyond 1. You can end up with, depending on the way you extract the stuff, you can end up with d of S getting multiplied by a constant. You got to make sure that the peak value of gamma of S never exceeds 1. Okay. So, I will go through with an example to illustrate, but this must be the form of gamma of S, which means that Zn of S, again you have the plus minus depending on whether you are doing even or odd, right. So, Zn of S will therefore be for example d of S plus s bar n divided by d of s minus s bar n. All right. Okay. Now I've made the assumption that z naught equal to 1, which means Zn of s will be numerator plus denominator divided by minus numerator plus denominator. Is this clear? Okay. Now, rather than deal with n, let's deal with a specific example. I will choose example n equal to 3. I will choose an inverse Chebyshev filter with omega s, the stop band edge being 1 radian per second as usual, and I will choose the stop band attenuation to be, say, minus 40 dB. Okay, this is all plotted on the log plot. So at DC it will be 0 dB, and we know that we will eventually scale this down by a factor of half. So the normalized magnitude response therefore will look something like this. Correct? And what will be the zero of transmission? Does somebody remember? Yeah, and what is that? The zero of transmission is given by cos of 3 cos inverse 1 by omega z equal to 0, which means this must be 2m plus 1 into what? Pi by 2. So the first value is pi by 2, which means that 1 by cos pi by 6 is the zero of transmission, which is what is 1 by cos pi by 6, people? 2 by root 3. Okay. Now gamma of s is therefore s cube divided by the inverse Chebyshev denominator. Okay. And what is the denominator? The denominator is given by, what I have done is I will get MATLAB into the picture, and it turns out that I don't know if you can read it. Can people in the back rows read the fine print in the MATLAB window, or what? You can, you cannot, or you don't know that you can or you cannot? Yes? Okay. So B comma A is Chebyshev 2, 3, 41 S. What that means is that B and A are the coefficients of the polynomials. Second order, this inverse Chebyshev is also called the Chebyshev type 2 response, and third order 40 dB of rejection in the stop band, cutoff of 1 hertz, and it's a MATLAB can do digital analog filters, so the S specifies an analog filter approximation, and as we expect, the numerator is S square, 0.03 S square plus 0.04, okay, and that is of the form. So where do the zeros of the numerator, the numerator has got zeros at? Timir, at what frequencies? It's basically 3s square plus 4 plus 4, which means that this goes to 0 at plus minus j 2 by root 3, which is what we calculated anyway. You understand? Okay. So, this proves that what? MATLAB is right. Okay. You understand? And the denominator, which is s cube plus blah 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 blah. So, I will just pick off the denominator here. So, this is s cube plus 0.6746 s square plus 0.2271 s plus 0.04. Okay. And one thing I would like to point out at this point is that you shouldn't, one common mistake when people do hand calculations is the following. You tend to keep rounding off stuff, these numbers, at any place convenient. It will turn out that if you, for example, the question is, what I am trying to say is, okay, do we really need to carry forward this 746, or should I just say s cube plus 0.6 s square plus 0.2 s plus 0.04? You understand? So, it turns out that the synthesis of the impedance, okay, is what is mathematically called an ill-conditioned problem. In other words, finite precision errors in all these numbers will basically propagate throughout the synthesis procedure, and if you keep truncating stuff right away, what will happen is that suddenly when you are going through the synthesis procedure, yesterday we saw that everything turned out nicely, right? So, you subtract this and then you take the residue and then things magically cancel and so on. The moment there is round off error, that stuff will not, that cancellation will not happen properly, and eventually if you have a high order filter, suddenly you will start seeing negative inductances and negative capacitances coming out of the procedure, right, even though you have not committed any arithmetic goof. Okay. The reason is that it turns out that can be shown that this whole process of generating the network from the reflection coefficient is what is called, I mean, it's a very sensitive process to the numbers here, and therefore it's mathematically what is called an ill-conditioned problem, which means that you can't simply truncate these numbers at after the first decimal place and hope that things will be okay. A rule of thumb is to keep as many decimal places as the order. For hand calculation, and when you are doing all this in a computer, of course it does not matter, because today there is no problem with precision numbers at all. Is this clear? Yes, sir.
Sir, ignore this statement. Then is it like if we change the impedance a lot, so even this won't change that?
Yes. So, if you change the impedance a little, I mean, a little, I mean, well, a lot. Well, I don't know about a lot, but see, but this is only a numerical computation procedure, right? So, if you change the impedances, a little bit, yeah, you should expect that the reflection coefficient doesn't change very much, okay. And in fact, we'll prove this later on, that if if you change the inductors and capacitors by small amounts, especially in the passband, you'll find that the response, the sensitivity of the response to small changes in the inductors and capacitors is actually very, very small, and you will show this by simulation. All right. So, and here please note that the 0.04 is not because I have truncated it to two decimal places. The actual stuff is 0.0400 something something, and basically I have been a little more conservative. This is a third order filter. I guess it would be sufficient to have to keep 3 decimal places and keep moving along, but I have taken 4 anyway. All right. So, what is Zn of S? is 2s cube plus 0.6476 s square plus 0.2271 s plus 0.0400 divided by 0.6. Oh, sorry. Another thing to do is not to make these mistakes, which is carrying stuff from top line to bottom line. All right. So now what we are trying to do is see if how we can determine the values of L1, L2 and L3 from this expression for Zn, right? So one thing that's clearly apparent is what? Can you comment on if we can use this on the following? Can we use the same trick that we used last time? Last time what did we say? As s tends to infinity, the network, the all pole ladder tended to just the first inductance, correct? Which means that you just set z into infinity, the expression z into infinity, find L, okay, and do the same thing in the network and equate the two. Can you now comment on whether that's possible now? No, look carefully. It's not possible because because L2 is there, that's correct. So what is Zn as s tends to infinity? What does the network tell you? L1 plus L2 parallel L3 must be 2 by 0.6746, correct? All right, but we don't know L2 or L3. You understand? Okay, but please note, so it's not immediately obvious that, while this is an equation, it's not uniquely giving us the value of L1 like the last time around. Okay, pardon? What is it that you're not able to understand? Can you? Yeah, so as okay, the question is how did you get as s tends to infinity, the looking in impedance tends to L1 plus L2 parallel L3. So as s tends to infinity, what happens in this series arm? Why is it L2? Capacitor is shorted, okay. And what about this arm? The series, the impedance is SL3 plus 1. So at very high frequencies, the SL3 is much larger than unity. Therefore, you can approximate this by simply SL3. So is that clear? So the equivalent impedance looking in at high frequencies is therefore L1 plus L2 parallel L3. Is that clear? Okay. Now the next the observation to make is that we continue pretty much the same way as we did last time. And what did we do last time? We said that at infinity, when we had the all pole ladder, this impedance looking in here would tend to 0 at some frequency which happened to be infinity, correct? All right, and we got L1 by equating the impedance of Z1 of S to, you understand, earlier Zn of S was given by SL1 plus Zn1 of S, okay, at S equal to infinity. Zn of infinity is SL1 plus Zn1 of infinity, okay, or L1 into infinity if you like. Is this clear? That's what we did. It turned out that Zn1 of infinity was 0, okay, and L1 was simply the limit of, was this guy divided by S as S tends to infinity. That's what we did earlier. Okay, now what happens? What do you think you can do? Now at S equal to? Very good. So at now what happens? Zn of S is nothing but SL1 plus Zn1 of S, correct? Which means that what? Zn of plus J2 by root 3, or let me in general J omega Z must be equal to J omega Z times L1 plus Zn1 of J omega Z, correct? I mean, this is exactly the same as what we did earlier. Earlier the zero of transmission was occurring at infinity, so everything was easy, okay. Here now you need to do stuff at J omega Z. So, and what is this now? What is Zn1 at J omega Z? 0, because of the series LC network. So, J omega Z times L1, okay, must be equal to Zn evaluated at J omega Z. Is this clear? Okay, I think I'm going to run out of time. So I will stop here at this juncture and we'll continue on Monday. Monday afternoon we meet at what, 2 o'clock? Okay, 2 o'clock in this room. Please bring your calculators. Let's go through this, all of us together, right? It's kind of, you also won't feel the, it's very likely that I make errors on the board, and after half an hour you find that we made a mistake. So I prefer that all of you bring your calculators so that multiple people are doing the same calculation, so that by redundancy we make sure that the whole process is error free. You understand? All right.